Okay, let me begin by just reviewing some topics. Maybe also I'll make a comment that the test on Monday, that's due on Monday, I'll be handing it out on Sunday morning. It'll cover everything up to section 10, section on probability. I'm just going to review the concept of a random variable. A random variable is some numerical quantity whose value is determined by the outcome of a random experiment. So in the background, you have a random experiment. The outcome of that random experiment will determine the value of the random variable. Now you have two types of random variables. Ones that are discrete. These are usually isolated points on the real line, integers usually, and those that are continuous, whose values will range over a continuum. Now, the mathematical description for a discrete random variable, it's described by a function called the probability function. It gives for every possible value of x, the probability of that value. If x is not a possible value, p of x is 0. The mean of a discrete random variable, it's the sum of the overall possible values of x times its probability. So it's a weighted average of the possible values of x. The weights are the probabilities attached to each x value. It's the long run average value. If you observe a random variable large number of times, p of x will be the proportion of times that you observe x. So the long run average value of x will be equal to the mean. It's also the center of gravity. If you consider the probabilities as weights placed at each value of x, that system of mass will balance at the mean. The other descriptors that measures the variability of a random variable, the variance, there you subtract off of each possible value of x, the mean, square it, and multiply, weighted by the probability. The last two lines in this slide are really computing formulas for sigma squared. The standard deviation tries to get the dimensions of variance back to the dimensions of the random variable. The standard deviation is just the square root of the variance. The binomial distribution. This is an important discrete distribution. It occurs if you repeat a success-failure experiment a number of times, n times. P is the probability of success. X is the number of successes in the n repetitions. You can derive the probability of each possible value of x. The possible values of x are 0, 1, 2, up to n. The integers 0, 1, 2, up to n. The probabilities of those values are computed by this formula. N choose x, p to the x, 1 minus p to the n minus x. The mean and variance. Now, the mean and variance could be calculated by these formulas using the value for p of x, but mathematically, it can be shown that the mean for a binomial random variable is simply n times p. This is a simple way of calculating the mean, n times p. The variance is n times p times q, n times p times 1 minus p. The standard deviation is the square root of that, square root of n times p times q. So this is the easy way to compute it for the binomial distribution. For any other distribution, you have to use the more complicated formula. Probability distributions for continuous random variables. They're described by what's called a probability density curve. In the discrete distribution, the total probability of 1 is broken up and placed at isolated points, usually integer values. For a continuous distribution, the total probability of 1 is smoothed over an area. The probability density curve gives you the density of probability at over each value of x. The total area under the curve is 1, and the area between 2 points is the probability of finding of the random variable being between those 2 points. So where the density curve is high, in an interval that's under that part of the distribution, that'll have a higher probability than when over an interval the same length and where the density is low. To compute the density, in actual fact, you have to use calculus, but this has been done for a lot of distributions and are tabled. An important distribution is the normal distribution. The normal distribution is a bell-shaped curve. So centered at some value mu. So random variables that have this distribution are going to be scattered about the value of mu. If you do a histogram of data that comes from this distribution, it should be able to estimate this distribution. It's the most important distribution in statistics. Many continuous random variables will have a normal distribution or approximately a normal distribution. There's a graph of the normal distribution. It's centered at mu. The standard deviation is the distance to the inflection points, where the curve changes from concave down to concave up. So the normal distribution, it's a bell-shaped curve symmetric about its center. The points of inflection on the bell-shaped curve are mu minus sigma, mu plus sigma. This is one standard deviation from the mean. The area under the bell-shaped curve between those 2 points, mu minus sigma and mu plus sigma, I'll go back to the graph. That's about 2/3. The area under the curve, if you go from mu minus 2 sigma to mu plus 2 sigma, is about 95%. It's close to 100% when it's between mu minus 3 sigma and mu plus 3 sigma. So there are many normal distributions, differing in mean and standard deviation. There's the normal distribution. Its mean is 100. Its standard deviation is 40. Here's another one. It has a different mean. Mean is 140. The standard deviation is about half of the other one, so it'd be 20. There's one that has a mean of 100, standard deviation of 20. Notice that if the standard deviation is smaller, you have to, the normal curve is higher so that the total area is always equal to 1. So for every value of mu and sigma, there's a different normal distribution. An important one is the standard normal distribution. That's where mu is equal to 0, sigma is equal to 1. Its area under the standard normal distribution, it's tabled, and that can always be converted. For other normal distributions, that area can be converted to area under the standard normal distribution. So there are infinitely many normal distributions depending on mu and sigma. One important one is the standard normal distribution. If x has a normal distribution with mu, mean mu, standard deviation sigma, If I subtract off mu and divide by sigma, this will have a standard normal distribution. This transformation is called the Z-score transformation. So you can convert area under the normal distribution with mean mu, standard deviation sigma, to area under the standard normal distribution. You do that by using the Z-score transformation back here. So suppose I want the probability X is between A and B. That's the area under the normal distribution with mean mu, standard deviation sigma. I perform the Z-score transformation on A, on X, and B. That converts X to a 1 under the standard normal distribution. That computes the two limits A and B to the corresponding limits under the standard normal distribution. So there's the normal distribution with mean mu, standard deviation sigma. It's centered over mu divided by sigma. That's the standard normal distribution. Those two areas would be exactly the same. This allows areas for the normal distribution to be just tabled for the standard normal distribution. So this is how you use tables. The tables are posted on the Stats 245 webpage. The table that's given gives the area from minus infinity up to Z for various values of Z. There's a portion of the table. I want the area between minus infinity and 1.45. That's this shaded area here. If I go into the table, the value of Z is 1.4. The top gives you the third digit. There's the 1.45. Looking down, you get 0.9265. That's this shaded area here. This can be computed for most values of Z. Another example, suppose the area you want is the area below minus 0.98. So you just go to the table, you look up minus 0.9, and then the other digit you go along the columns, and that's the area that's asked for. The area that you'll find is 0.1635. You can compute other areas quite easily. Suppose I wanted the area above 1.45. That the shaded area is here, but this is the tabled area. It gives you the area below. So you can always compute that because it'll be 1 minus that tabled area. 0.0735 is the shaded area. If I want to find the area between 2 points, I look up the area below 1.45. So I'm going to go 0 and 1.45. That's the area that I want. Look at the table 1.45, get 0.9265. That would be everything below 1.45. So I have to subtract off the area below 0. You don't have to look up that value because 0 will divide the area in half. The area is 0.500. So the area between 2 points is the difference in the two tabled areas. You can use the fact that the area above 0, the area below 0 are both 0.500. I think it's a good idea when doing these problems to do a little sketch and sketch the area that you want, and then you can sort of determine how to compute it. Suppose I want the area between minus 1.26 and 0. The area below 0 is 0.500. The area below minus 1.26, that's in the table, that's 0.1038. So the area in between is the difference. The area between minus 2.30 and 1.80. This is 1.80 here. This is minus 1.2 minus 2.30. If you look up 1.80, you get 0.9641. The area below minus 0.23, you have to subtract off. That's 0.0107. So the area in between is the difference in those values. Another example. Z, I want the area between minus 1.4 and minus 0.5. Look up the area below minus 0.5, you get 0.3086. Look up the area below minus 1.40, you get 0.080. It's always useful to draw a rough little diagram of the area you're trying to compute. Computing areas for the standard normal distribution, for general normal distribution approach is to convert X to its Z score, convert the limits to their Z scores, convert the area under the normal distribution with mean mu, standard deviation sigma, to area under the standard normal distribution. There's a formula that the area between A and B is the area for Z, after I perform the Z transformation, is the area between A minus mu over sigma, B minus mu over sigma. Suppose a man aged 40 to 50 is selected at random from a population. Suppose I'm going to measure the blood pressure of the man. X is a random variable because it'll depend on which man was selected. Assume that X has a normal distribution with mean 180, standard deviation 15. So that means that X will be coming from underneath a bell-shaped curve, standard at 180. The sigma determines how spread out that distribution is. Suppose I want to calculate the probability that X is between 170 and 210. So here I've drawn the normal distribution with mean 180, standard deviation 15. Gains, the standard deviation is the distance from the mean to the point of inflection. That's the area that I want. So I perform the Z transformation on everything, on X, on A and B, and I convert this to area under the standard normal distribution. These are just the standard scores of the limits, minus 0.667, 2.00. Then we can use the table to calculate that. There's the area that I want. There's the corresponding area under the standard normal distribution. Another example. Suppose a bottling machine is supposed to fill bottles with 32.0 ounces and a standard deviation of 0.02. So that means that the amount that's put in the bottle will be centered around 32, sometimes above, sometimes below. This tells you, the standard deviation tells you how spread out that number will be. With that information, find the probability the bottle contains between 32 ounces and 32.025 ounces. Find the probability that the bottle contains more than 31.97 ounces. The solution: convert those numbers, limits, to their standard score. So 32, its standard score is 0. The standard score of 32.025 is 1.25. There's the area asked for. The limits down here are whether the distribution up here is the one in question, or whether it's corresponding standard normal distribution. There is the computation. So first step is to convert things by doing the standard score transformation, subtracting off the mean, dividing by the standard deviation. That converts this random variable into one that has a standard normal distribution, and converts the limits 32 and 32.025 into the corresponding limits. That area can be looked up by looking up the table values. The second question was, what's the probability that x is greater than 31.97? Doing the standard score transformation, that's the 31.97 turns out to be minus 1.50. The area below minus 1.50 is 0.668. So the area above is 1 minus that. Summary. For random variables, there's two types: discrete and continuous. Usually if the random variable has integer values, it's a discrete one. If it varies over a continuum, it's a continuous random variable. The probability distribution for a discrete random variable, that's described by the probability function. For a continuous one, it's described by a probability density function. There's the probability function of a binomial random variable. I think it has a n equal to 10 and p equal to, might be 0.85 or I don't know. There's how you calculate p of x for a binomial random variable. This is how a binomial random variable exists. It's the number of successes in n repetition of a success-failure experiment. The probability of success is p. There's the formula. So usually you have n time points, and at each time point you can have a success or a failure. P is the probability of success at each time point. N is the number of time points. X is counting the number of successes in the n time points. To show you that there's other distributions, sometimes the events are occurring in a continuous time interval, and the chance of the event occurring at a point, this might be uniform across the time point, or across the points of time. So there you can have an infinite number of possible time points where the event can occur. This has what's called the Poisson distribution. We won't be looking at that. Ours will just be where you have successes occurring at time points 1, 2, up to n, and p is the probability of success. So there's a discrete case. The probability distribution of a continuous random variable, it's described by a probability density curve. Here I've drawn a probability density curve. It actually, this one has two modes, high points. This is probably because there's two populations mixed together, two normal populations mixed together. One resulting in this high point, the other resulting in this high point. The total area under a probability density curve is 1, and when and the probability between 2 points is the area under the curve between those 2 points. The normal probability distribution. It's probably the most common distribution come against. It's a bell-shaped curve, so it's symmetric about its mean. The standard deviation is really the distance to the points of inflection. So if you have a larger standard deviation, the curve will be more spread out. The total area under the curve will always be 1. You can use the normal distribution to calculate binomial probabilities. That's because if you look at the distribution, the binomial distribution, it approximately has a bell-shaped curve, except that the values are located at integers. So here's the binomial distribution. It's described in the rectangles. This is the binomial distribution with n equal to 20, p equal to 0.70. So the mean is 14. There's the normal distribution with the same mean, same standard deviation. It'll approximate the binomial distribution. I spread out the binomial probabilities. They're actually at isolated points, integer points. I've spread them out so that they touch. So there's the formula for approximating binomial probabilities by a by the normal distribution. X has a binomial distribution, n equals parameters n and p. Y has a normal distribution with the same mean, same standard deviation of x. The probability that x equals a will be an integer, is approximated by the area under the normal curve between a minus a half and a plus a half. The minus a half and plus a half is called the continuity correction. It's because you're approximating a discrete distribution by a continuous distribution. There is the binomial probability that x equals a. I've spread it out so that it goes from a minus a half to a plus a half. There is the normal curve having the same mean and standard deviation as x. There is the area under the normal curve between a minus a half and a plus a half. That's going to approximate p of x equals a. That's example. X has a binomial distribution with n equal to 20, p equals to 0.70. We want the probability that x equals 13. We could compute that using the formula for binomial probabilities. 22 is 13, 0.70 to the 13th, 0.30 to the n minus 13, 0.1643. This becomes complicated when n is large. Say if n was 2,000 and x was 130, this computation would be a lot more difficult. But this is why one uses the normal approximation. Normal approximation, you choose a normal random variable, has the same mean and standard deviation as x, and you find the area under that normal curve between 13 minus a half and 13 plus a half. If I do that, I get 0.1725. The exact value using the binomial formula is 0.1643. This becomes more accurate as you increase the values of n. N was equal to 20 here. If you increase the value, say, to n equal to 2000, okay, the normal approximation is approximately the same as the exact value. The normal approximation, when I'm working out the probability x is between two integer values, a and b, it'd be p of a plus the next one up to p of b. That can be approximated by area under a normal distribution between a minus a half. The lower limit, you subtract a half. The upper limit, you add a half. X has a binomial distribution, n equal to p, and parameters n and p. Y has a normal distribution with the same mean standard deviation of x. The 1/2 is called the continuity correction. It's because we're approximating a discrete distribution with area under a continuous distribution. Here, the rectangles here are the binomial probabilities. I spread them out so that they range from an integer minus a half to an integer plus a half. So the area between the sum of the probabilities between A and B, this would go from A minus a half to B plus a half. There's the approximating area. Example, suppose X has a binomial distribution n equal to 20, P equals a half. Now let me point out that the normal approximation for that value of n is a little bit off. But as n increases to bigger and bigger values, the normal approximation becomes almost exact. I want to find the probability x is between 11 and 14. So if I was using the exact value, I'd work out p of x, p of 11, p of 12, up to p of 14. There's the exact formula. That works out to be 0.5357. Use the normal approximation. I approximate x by a normal distribution with the same mean and standard deviation of x. And the limits become the lower limit minus a half to the upper limit plus a half. So I'm doing that calculation. I get 55.12. The exact value was 0.5357. Now, where this becomes very useful, here we had n equal to 20. If you had n equal to 2000, and these values here were 110 to 140, you have to compute the exact value for 110, 111 up to 140. It'd be a lot of work. Normal approximation becomes a lot less work, and it is almost as accurate as the exact value. So the accuracy of the normal approximation to the binomial distribution increases with the value of n. There's the formula for the normal approximation. Again, the 1/2 is called the continuity correction. It's because you're approximating a discrete random variable which has probabilities located at, say, integer values by a continuous random variable where the probability is spread over a continuum. Example, suppose the success rate for an I operation is 85%. Suppose the operation is performed 2,000 times. So this, and we'll let X be the number of successful operations. The number of successful operations should be approximately N times P. P is 0.85, N is 2000, N times P would be 1700. Find the probability that number of successes is between 1650 and 1750. Now, if you're using the binomial formula, you'd have to compute that for 1650, 1651, up to 1750. The next one, what's the probability number of success? Is at most 1800. At most 1800 would be 0, 1. No, it'd be 1800, 1801, 1802, up to 2000. So this is an example where the normal approximation becomes a lot easier. Y has a normal distribution with the same mean and the same standard deviation as X. The probability that X is between 1680 and 1720, that would be 1680, 1681, 1682, up to 1720, is the probability that Y is between 1679 minus 1680 minus a half to 1720 plus a half. Mu of Y and mu sigma of Y is 1715.969. So using the normal approximation, the limits become under the standard normal curve minus 1.8 to 1.28. You'd have to then look up the area below 1.28 and the area below minus 1.28, and the area between would be the difference. The second part, probability X is equal to 1800. If I was using the exact formula, I'd have to do it for 1800, 1801, 1802, up to 2000. So it's a lot easier to use the normal approximation, and the normal approximation will give you an answer that's almost correct. There, I get the probability that Z is less than or equal to 6.29. 6.29 is about beyond the tables. The area below that is virtually 1. Maybe we'll stop at this point, and I'll allow you to ask questions. First of all, I'm going to share the screen.
Hi, Professor. I have a quick question.
Sure.
Okay, can you explain the difference between like the binomial standard distribution theory, like how it's different than normal? Like
Okay, the binomial distribution is a discrete distribution. How it arises is you have a success-failure experiment that you repeat a fixed number of times. The fixed number of times is N. Chance of success is P. The chances of failure is 1 minus P, or sometimes called Q. And X counts the number of successes. So for example, if I performed an eye operation 2,000 times, and the chance of it being successful was 85%, 0.85. And I counted the number of successes in the 2,000 repetitions. That would have a binomial distribution. The normal distribution usually occurs when you are taking a continuous random variable. Quite often, a continuous random variable will have a normal distribution. If you're taking data from a normal distribution and you plot a histogram and the histogram is bell-shaped, then probably the data is coming from a normal distribution. And quite often people make that assumption that it's coming from a normal distribution.
Okay, that makes more sense.
Yeah. So
Okay.
the normal distribution is a continuous distribution. The random variable will be varying over a continuum, and it'll be following a normal pattern.
Okay, thank you.
Quite often, things don't have a normal distribution. For instance, in modeling the stock market, each day there's a change in the stock market and the stock's price. That change sometimes comes from a bell-shaped distribution, but sometimes it comes from a distribution that has heavy tails, meaning that sometimes there's big gains or big losses. So people who are betting on the stock market, they use that, they try to model it correctly to take into account the extremes. Anyway, other things like if I measured the person, if I took a person, picked a person at random, say he's 18 years old, okay? He's male, 18 years old. There'll be, the height of that person will probably be following a bell-shaped curve. That would have to be tested, okay? Anyway. So are there any other questions? So quite often, the data is assumed to have a normal distribution that's collected in practice. In some cases, there's been fraud, and people have actually manufactured their data by randomly generating it from a normal distribution. They've been found out because there's tests that can tell you whether it fits too close to a normal distribution than in actual practice. So people who've manufactured their data have been found out by statistical methods. Okay, well, if there are no more questions, maybe we will end the lecture at this point.